Good morning, everybody. I decided to go ahead and put together a video for you guys just to talk through the lesson that we would have done in class. So if you guys would just go ahead and open up your slideshow today, we're going to be working on this idea of circular motion, do a little review from our previous concepts that we looked at last class, and then we're going to get into some applications. So homework today is going to be to work on the practice problems set and use your Friday time also to split up the work with that. That's going to be due by Sunday. Cool. So get yourselves ready by getting out your circular motion formulas. And let's start with just a quick little experiment. In class, we had a bunch of stuff around, and you were to go find one of the objects and then figure out the period, frequency, angular velocity, linear speed, and centripetal acceleration of that object. So look through your formulas to remember how to get through all those things. And use this FET right here. The FET is just a record player, and it shows like a little ladybug on it. But for the most part, when you get through these quantities here, you just need to get a timing from it. So using a stopwatch on your phone. And you also need to have some sort of way to measure distances for radiuses. And in the program, they actually give you a ruler. So all you need to do is pick one of these and just go through it, figure out what are all these variables for that one thing. Okay. All right, so today we're going to be looking at centripetal force and how this relates to different types of circular motion. So our formula that we're really going to focus on today is going to be F equals mv squared over r. That is called the centripetal force, and it provides a net force. So let's take a look at our ideas. So what I would do to start with today is get out your circular motion practice problems, open those up, because you can go ahead and problem solve as we work through the slideshow and get started in on this lesson. So working through, you can also use your textbook. We have our online textbook, and you can use pages 252 through 257. That's going to help you with these problem-solving problems also, so just an additional resource. So the way that we solve problems with circular motion is we always want to realize that whenever an object is going through circular motion, that object is accelerating. It's called a centripetal acceleration. It's always directed towards the center of the circle. Now, when an object is accelerating, it's doing so because there's a net force acting on the object. That's Newton's second law, F equals ma. Okay. Now, in the case of circular motion, that ma, that net force, we define it as mass times velocity squared divided by radius, mv squared over r. That's always going to be our net force. So when an object is going through circular motion, you ask yourself, what is providing the net force? So for instance, like a planet going around the sun, the net force would be provided by mg, or weight. For a friction turn in a car, you're going around a corner and your friction on the road is helping you on. mv squared over r is being provided by friction on a flat surface. We call that mu mg. When you have a ball spinning on a string, we call that force that's holding it in the circle tension. So you notice mv squared over r equals tension. And for a roller coaster, we're going to see how the normal force acts as a centripetal force. And there's some irregularities about how the normal force acts at the top versus the bottom of a roller coaster ride. And so we end up having normal force plus or minus mg. We're going to explore that one here in just a minute. Okay, so our first topic to explore here, which is also on page 253 in your textbook, this one here is how does a car make a turn using friction alone? So this is sometimes we call this a flat turn because we're not concerned with angles on the road. We're just on a flat road. The only thing that's keeping you into your turn is friction. And so you're going to work through these problems here. Now, as you work through them, I've put down here in the speaker notes, put some clues to help you out. Okay, and the answers. And then on the next page, I went ahead and just showed you the final answers. This is stuff we worked out together in class, but I want you to work it out on your own. So put your thought into it first before you check out the answers. Can you figure it out on your own? And then go through and check the answers and see how you did. But the idea here is get on top of these concepts, learn them, understand how to apply these. Now, when you're finished with that first question there, go ahead and look at questions 5 through 7 in your uniform circular motion practice problems and see if you can do those. Okay, next situation we have is one of a banked turn. And so we talked about friction, okay, but there's also another way to help you go around a turn in a car, and that's to bank the road. Now, banking is like what this bus is doing right here. The road itself is tilted, and then as the vehicle is going around that turn, it's actually a component of the normal force. okay, that is supplying the ability to turn. It's applying the centripetal force. So again, in page 350, 253 and 254 in your textbook, it'll go over these details if you want to look at it with more depth. But take a look at this picture. So notice that the car is on a turn. It's driving into the screen, and the normal force is providing a push upwards, and of that push upwards, the y component of that push, the cosine component, is equal and opposite to the weight of the car. The reason for that is because the car is not accelerating in the y, it's not accelerating up and down. But the horizontal component right here is an unbalanced force. Okay, an unbalanced force is a net force. And in this case, this net force is the centripetal force. Okay, so if you notice this diagram right here, it's not balanced. The car is actually accelerating to the left, and to the left is the direction of the radius. It's turning the corner that has the radius to the left. Okay, now when we look at how to break up this problem and actually solve questions with it, you need to realize that the mg, the weight of the car, is equal to the y component of the normal force. And so what I do is I take that y component called n cosine of theta, and I replace it with its equivalency of mg. And the sine component of the normal force is unbalanced. It's by itself. It's providing the centripetal force. And so I notice my net force, which is supplied by n sine of theta, is the centripetal force. Now I want to go ahead and redraw that as this triangle here. So notice the triangle. This is your key to these problems. You've got your angle, you've got your mg, and you've got your mv squared over r. And now we're just doing trig. Okay, so you've got yourself a triangle. You understand what's going on. Answer those two questions. I've talked it through in the speaker notes, and I also have the key. And you just want to be able to work that out and then practice it yourself in the practice problems for number 13A. Now, once you've done 13A, we can mix those two skills that we just looked at, but it's pretty complicated. So I have an extra credit question in there. There's an online resource to look through the math with it. But with the extra credit, you're basically saying something to the effect of, if a car is going around a banked turn, they can go around that bank turn not relying on friction at all if they're going exactly the right speed. But if you're going too slow, then the car almost like wants to slide down the slope, and that would cause a frictional force to develop going up the slope. Okay. Or if you're going too fast, you'd want to slide up and off the slope, which makes a frictional force develop going down the slope. Okay. So notice in this free body diagram, I would have had to assess, first of all, what's the ideal speed for the car based on the previous problem with the angle of the slope that's there. And then I would say, okay, it looks like the car is going too fast. Therefore, it's going to slide up. Therefore, the friction goes down the slope. And notice how I went ahead and drew a new arrow here for friction. Okay. Now, what I have in this picture, I've got three real forces. I've got normal force, friction, and weight. And then I'm going to take my components and put everything into x's and y's. So I break up my normal force into x's and y's, and I break up my friction into x's and y's. And then I set up two equations. My first equation says the sum of the forces in the y is equal to 0. The y aspect of this is in equilibrium, and that's because the car is not accelerating up or down. Okay, but the x component is not in equilibrium, so that x component equals mv squared over r. And then I actually write out these two expressions. Now, the thing that makes these problems really hard is that you need to solve this first expression right here for your normal force, and you come up with a pretty complicated expression, which you then substitute as the normal force in the next problem for the unbalanced part of it, and then you just work it through with algebra. It's pretty tense with the algebra, but you give it a try. Okay, the extra credit for sure. That's the extra credit. It's in your practice problem set. It's 13B and C. All right, now that you've got that, let's get into this idea of tetherball. Take a look at the two videos. They're kind of fun. And then we're going to look at a tetherball example. So tetherball, when it goes around a pole, it's actually performing circular motion. So if you notice as it swings in a conical shape, okay, as it goes around, the base of the shape, the horizontal aspect, traces out a circle. And that's the circular motion we're looking at, that ball going around in that circle. Now, the ball itself has actually got tension that's holding it to the pole, but it also has weight going down. Now, notice I can break the tension of these components. Now, the component that I call T cosine of theta, that component, that has to be equal and opposite to the weight component. The reason for that is because the tether ball, if it's in uniform circular motion, is not accelerating up or down. Okay, it's just kind of maintaining altitude, but it's accelerating inwards all the time. That's what's keeping it in the circle. So this T sine of theta is what supplies our centripetal force. So try this problem right here. You're going to break it up into parts. The goal here is to make a triangle with all of your component vectors correctly, and you notice there's like a process here to do it. And of course, I do have the key on the next page too. But try it yourself first, then check out the key, and then try number 11 in the practice problems. Okay. All right, next thing we're going to look at is this concept of vertical circular motion. And notice how this airplane is like flying up, and then it goes through this like loop and goes down. Okay. And if you notice as it's doing that, it actually has a point right up here. If you were in this airplane, where when you're going from up to down, you would actually feel like you're temporarily floating for a second because the way the forces are working as you go through this circle at the correct speed. When you go down and then start climbing up really quick, when you're in the bottom there, you'd feel like you're extra heavy in the airplane. Feel like you're getting pushed into the ground. So I want you guys to watch this video. It's really fun. And it kind of shows this thing's called the Balmer Comet, but it leads us into this understanding of what is vertical circular motion. Now, we're going to look at two different applications, of vertical circular motion. First one here is when you're going around a vertical circle, like on a roller coaster ride. And let's say you're in a roller coaster, and at the top of the roller coaster, you have the floor of the car that you're in. It's like above you because you're upside down as you go around this loop right here. Now, that floor is actually still pushing you down into the center of the circle, and weight is also pushing you down. So the support force, the normal force, and the weight, both of those are working together to provide the centripetal force for you. And so you notice when you're at the top up here, your centripetal force is equal to the combination of those two forces, the normal plus mg. So what you're going to do is use this data right here and just tell me what is the normal force. Okay. You'll do something similar to this one here, where now you're at the bottom of the track. When you're at the bottom of the track, if you notice the normal force and the weight are in opposite directions. Okay. And so your net force is actually the normal force minus the mg in this case, because they're opposite directions. And so that turns into a minus problem. And then you go ahead and solve out for normal force here. And then in the next question, it shows you you're back at the top again, but you're going slow. Okay. You imagine if you're going too slow, you'd actually fall out of the cart here and fall into the middle of the circle. Really dangerous. So there's a point when the speed is at its very minimum before it's too slow. At that point, the normal force actually goes down to 0. And that's when you're ready to fall out of the cart right there. That speed is the minimum speed you could go around that loop there without failing. So what is that speed? All of those answers, by the way, are worked out here. And then it shows you numbers 8, 9, and 10 deal with those problems right there. So that's pretty much everything we're doing today, working through these concepts and getting on top of the applications for circular motion. So that's it, guys. You have a great day. Enjoy yourselves.